Okay, for this last lesson, we're going to take a look at infinite geometric series. Now, we're going to start with a very common example to explore how infinite geometric series work. So, David buys a pizza. He eats half the pizza, then half of the remaining piece, then half the remaining piece, going on and on and on and on and on. If it continues in this direction, it will look like he will never finish the pizza, because there will always be half a piece left over every single time. Why would this not be actually possible in practice? Because eventually the piece would be too small to split in half. If I'm representing the situation with a geometric series whose first term is 1/2, he ate half the pizza, then he ate half of that half, so 1/4, then he ate half of that quarter, so 1/8, and then half of that eighth, so that'd be 1/16. And then that would keep on going theoretically forever. Now, based on this series, the values of A and R, well, the first term is going to be 1/2, obviously. The common ratio, we've already said based on the problem, I'm eating 1/2 every single time. Which means that given my series formula, I'm going to take my first term, I'm going to multiply that by my common ratio to the power of n minus 1, and that's all going to be divided by my common ratio minus 1. Now, if I want to simplify this formula, I can simplify the denominator by taking that 1/2 minus 1 and saying that that would be negative 1/2. And because the top is being multiplied by 1/2 and I'm dividing by negative 1/2, I can actually take out the common factor here and state that this would all be the same as negative 1/2 to the power of n minus 1. Sorry, plus 1 in this case. When I apply that negative to the numerator, I got to apply it to both terms. Now, I could plug all this into my calculator to see what it's going to look like. So I can say that on my calculator, y1 would equal negative 1/2 to the power of x plus 1. And I can go into my table and see what every term value would be. So at term 1, it's going to be 0.5. Term 2 is going to be 0.75. Term 3 is 0.875. And then I'm going to keep going to 0.938, 0.969, 0.984, 0.992, 0.996, 0.998, 0.999. If I'm plotting these values out on the grid, then the sum of the first one was 0.5, then 0.75, then 8.75, then a little above 0.9, then a little above halfway for 0.9. And you can see that what happens is I keep getting closer and closer and closer to a specific value. It would appear that as I keep going and I keep increasing my n value, then I'm going to get closer and closer and closer to 1 every single time. We can even see it's trying to approach this value of 1. The term we have for this is a convergent series. The sum of all the terms keep converging or getting closer to a specific value. In this case, it's going to get closer and closer and closer to 1. We would say that if we went on to infinity, that the sum would be 1. Or instead of Sn, we say S infinity, going that it would keep going on to infinity. Note that the sum of a finite number in this term series will never actually reach 1 because it would have to keep adding and splitting that half going on for infinity. The number would get smaller and smaller and smaller and smaller and smaller, so it just theoretically going on forever would get so small that it would eventually just get rounded to 1 because it's so infinitesimally small that we wouldn't really be able to measure it in a meaningful way. Now, why does that work with a pizza? Well, in reference to the pizza, if I keep eating half over and over and over and over and over again, eventually it's going to get too small to split again, and the whole pizza will be eaten. That's why they use the pizza method, because eventually you have to finish off the entire pizza. No matter how small you bite it down, then it would eventually, if it kept getting smaller and smaller and smaller, just consume one whole. What if I had a different geometric series? In this case, my geometric series is 2, 4, 8, 16, going on forever. Well, my first term is 2. My common ratio is 2. So my sum is going to be term 1, which is 2, times the common ratio 2 to the power of n minus 1, all divided by the common ratio 2 minus 1. I can simplify this if I am doing 2 minus 1 in the denominator and say that it's going to be 2 to the 2n minus 1, all divided by 1, or just 2 and 2n minus 1. Now, if I put this in my graphing calculator, I'm obviously going to say that y1 is equal to 2 times 2 to the power of x minus 1. I can go to my table to see what these values are real quick, and I'm going to have the first term is 2, the sum of the first 2 is 6, sum of the first 3 is 14, and it's going to keep going. 30, 62, 126, 254, 510, 1022, and 2046. How does that work on a grid? Well, I'm going to start at 1 and 2, 2 and 6, 3 and 14, 4 and 30, 5 and 62, And then once I reach the 6th number, I've already launched off the grid. We call this divergent because continually the sum is getting further and further away from each other. So unlike in the last case where we saw it and the sum was getting closer and closer and closer to a specific value, in this case 1, now the space is getting further and further and further apart every single time. When things are splitting apart further, they are diverging. That's where the term divergent comes from. So, we have seen that an infinite geometric series with a common ratio of 1/2 converges to a particular value, and one with a common ratio of 2 diverges and does not have an infinite sum.